All right, let's look at an example for the Lyapunov theory, approximating basin of attractions. So we're going to consider this. We're going to consider. My pup's right here. You want to see? Jack, come say hi. There's Jack. He's so cute. Yeah. All right. I want the show. Stay right here. All right. No. All right. On with the show. Gotta watch him. Let's consider this system. X1 dot is equal to negative x2. X2 dot is equal to x1 plus x2 squared minus 1 times x2. Hey. All right, so let's linearize this system. If we linearize this system, we all remember how to do this, right? I hope so. So if we linearize this system, we're going to get A is equal to partial derivative of f1 over x1, partial derivative of x1, oops, x2 for x1, for f1. Oops, this is backwards. Partial of f1 for x2, partial of f2 for x1, partial of f2 for x2, right? And then this is solved at, we're going to say that the origin here is where we're going to look at. All right, so this is 0, negative 1, 1, and negative 1. All right. So what kind of system is this? Where are the eigenvalues? Well, let's find out. Let's look at the eigenvalues of this system. This is lambda I minus A. The determinant of that is equal to the determinant of 0, negative 1, 1. Oops. This will be lambda plus 1 minus 1 plus 1, lambda plus 1. All right, and then the determinant, and then we want this guy to equal to 0. So the determinant of this guy is equal to lambda plus lambda 1 plus 1. It's equal to 0. This is going to be equal to a lambda squared plus lambda plus 1 equal to 0. All right. And then if we put this in the quadratic equation, we should get the following. Lambda 1, 2 is equal to negative 1/2 plus or minus square root of 1 minus 4 AC, that's 4, over 2. So this is going to mean that we get that our eigenvalues are 1/2 plus or minus square root of 3j over 2. Okay. So what given these eigenvalues, what kind of system do we have? We have a Hurwitz matrix. Oh, it's not updating. Let me see if I can fix that. All right, so now I think we can see that. So let's go back for a minute. So we have this system. We're going to linearize the system. The linearized system is 0, -1, 1, -1, right? And then we want to find the eigenvalues of A to see what if our matrix here is Hurwitz, because if it's Hurwitz, then we can use this Lyapunov theory. So to do that, we're going to look at the eigenvalues of A. So that's this part right here. We want to make sure that this is equal to 0. This is equal to 0, which implies that this is the determinant of our system. This is the characteristic equation right here. And then we get the eigenvalues of our system as -1/2 plus or minus square root of 3j, or imaginary number, over 2. All right, and so now, because we have that our system, we have that these eigenvalues are negative definite, this implies that the origin is asymptotically stable. All right, so now let's do the fact that we can, the theorem that I presented last time, we can assume a value of Q and we're guaranteed to have a P. Okay, so let's take Q equal to the identity matrix. Okay, and then let's find P. All right, so now let P be equal to P1, P2, P2, and P3. Okay, and then we have A as above. A is equal to, where'd it go? 0, 0, -1, 1, and -1. Okay, now let's just say PA plus A transpose P is equal to P1, P2, P2, P3, A 0, -1, 1, -1, plus A transpose, so 0, -1, -1, 1, times P, P1, P2, P2, and P3. All right, let's keep this train going. We get, this will be P2, this will be minus P1 minus P2. The bottom one, this will be P3. And this will be minus P2 minus P3. Plus, let's do the same thing over here. Say P2. Oops. Minus P1 minus P2. This will be P3. And then it'll be minus P2 minus P3. Now this guy is going to be equal to A -1, 0, 0, 1. All right. So this will result in 2P2 minus P1 minus P2 plus P3 minus P1 minus P2 plus P3. And then this will be -2 times P2 plus P3. And now this will be equal again to the right-hand side. Make sure we draw these arrows here. Great. All right, so now this will result in 3 equations and 3 unknowns, right? So we'll get 2P2 is equal to -1 from the top. This is from element 1, 1. on the right and left. Then we'll get negative p. Let's go with element 2 or element 2, 2. So this will be negative 2 p2 plus p3 equal to negative 1. So this will imply that p3 is equal to 1/2 minus p2, positive 1/2 minus p2. p2 is equal to minus 1/2. So this will be minus 1/2, which is equal to negative 1. No, positive 1. Great. All right, and then the last equation that we need to solve for is, so this is from, oops, this guy is from element 2, 2. And then the last one that we have to solve for is negative p1 minus p2 plus p3 is equal to 0. And then this is from element 1, 2 or 2, 1. They're the same, as they should be the same. All right, so now we have p2 and p3. Let's solve for p1. So p1, negative p1 will equal to negative p3 plus p2, which is equal to negative 1 plus 1, negative 1/2. Yep. And this will be equal to 1.5, which implies that p1 is equal to negative 1.5. All right, so now what do we get at the end of this? We get at the end, p is equal to 1.5, 0.5, negative 0.5, and 1. This is our matrix P. We can also note, before moving to the next page, that the minimum eigenvalue of P is equal to 0.691. Great. All right. Okay, but what does this solution say for our physical system? So this V, because we had X transpose PX, which is equal to X transpose, sorry about the dog, 1.5 and 1 times X. Let me move all this over. All right. So then this guy will be equal to 1.5 times x1 squared minus x1, x2 plus x2 squared. So this is our resulting Lyapunov function using the P matrix that we found. All right. So now let's use the original system. X dot is equal to f of x. All right, what do we get? We get that v dot of x is going to be equal to 3x1 minus x2 minus x times minus x2 plus minus x1 times x1 plus x1 squared minus 1 times x2 like that. All right, and now if we put everything together, we'll get minus x1 squared plus x2 squared minus x1 cubed times x2 minus x1 squared times x2 squared. All right. So this first quantity right here is literally the norm squared. So this will be equal to negative norm of x. And now the guy on the right will be equal to the norm of x1. Well, this is all less than or equal to, right? x1, x2 times the norm of x1 minus x2, okay? And so this step right here comes from the fact that this comes from the fact that the norm of x1 is going to be less than or equal to the norm of x, okay? The norm of x1 times x2 is going to be less than or equal to 1/2 times the norm of x squared. And that's through Young's modulus, or Young's inequality. X1 minus x2 squared is going to be less than or equal to square root of 5 times x. Coming back from this guy, let's come back here. And then we get that this guy implies that v of x dot is less than or equal to negative norm of x squared plus square root of 5 over 2 times x norm to the 4th. All right, so now we can say that v dot is less than 0 for all x, for all x less than 2 over 5, which we're going to call r squared. All right. Now, using what we had before, the general framework I set up before, we can take C as equal to the minimum eigenvalue of P times r squared, which is equal to 0.691 times 2 over 5, which is equal to 0.618. Okay, so now we can say that for all v of x less than c, our system is guaranteed to converge to the origin. Great.